If you've ever heard about asteroid mining on the internet, the story usually goes something like this. There are nearby asteroids with so much gold and precious metals that they would be worth trillions of dollars on planet Earth. Our technology isn't strong enough to mine them yet, but in the near future we can use these resources to benefit Earth and build massive profitable space stations throughout the solar system. Well, the truth of the matter is completely different. Welcome back to the channel, guys, and in today's video I'm going to be explaining the basic facts and economics that make asteroid mining completely useless even thousands of years into the future. Okay, so the first thing we should say is that there are no giant nuggets of gold floating through space. All asteroids basically fall into these three categories of carbon, silicon, and metallic type asteroids. And the type that people want to mine are these metallic type asteroids. So scientists think that these are the cores of ancient protoplanets, and so these are mainly located in the asteroid belt, but they'll sometimes intersect Earth's orbit, and they're also very rare. Now, the actual abundance of precious metals is going to be very small in these asteroids. Most of the asteroid, probably up to 90%, is going to be made out of iron-nickel alloy, and then it may have some other rocks and metals. And then when it comes to the precious metals like silver, gold, and other platinum group metals, these are usually in the parts per million or parts per billion. Now, you may be thinking, are there layers of the core of these planets where silver, gold, and metals like this are much more abundant or even have their own layers? Well, unfortunately, it's not the case. And the reason is that all of these metals are what's called siderophiles, which means they like to bond with nickel and iron. So when you have a solid core, like what we have on planet Earth, all of those precious metals simply bond to the iron and nickel and make sort of a homogeneous substance. Now, the main reason that we know this is because of meteorites. So a meteorite should be the core of these metal objects, and what we see is very tiny abundances of platinum group metals and gold and silver. And of course, what we mostly see is iron and nickel alloy. We also have deposits like the Sudbury Basin in Canada, where giant asteroids have crashed and they leave behind a lot of these precious metals. Now, one of the reasons we have gold veins and other ore veins on Earth is because of geological weathering will basically weather these rocks, and then it'll lead to combining a lot of these precious materials into a higher abundance in certain areas. So in fact, many of the ore veins that we mine today are much more concentrated than what we see in asteroids. Now, the choice of which metal to mine would actually be pretty obvious. Gold is one of the most expensive of these precious metals, and it's also the only metal that has a big enough market where importing a lot of gold from space would not disrupt the size of the market and cause the price to decrease in a significant way. Now, since there are no gold veins on asteroids, the mining and refining would need to look like an open pit mine on Earth. The first step in this process is blasting and collecting large quantities of rocks and metal ore. Next, you need to crush the metal into tiny particles. After the crushing, there are many complex chemical steps to extract the gold, which include heap leaching with sodium cyanide, carbon adsorption, elution with sodium hydroxide, electrowinning, and finally smelting into gold bars. Most of these steps require the strong gravity of Earth, so it would of course be much more complex and expensive to complete on an asteroid. Now, based on my research, these are the ratios for how much mass you would need compared to the actual mass of refined gold you'd get in the end. So, just the basic equipment and refining infrastructure would be about 100 to 1,000 times as much mass. The explosives would also be about 100 to 10,000 times as much mass. And of course, there's tons of different chemicals that you would need to use in the process. Typically, this is at least 20 times the mass of the final refined gold that you use. And of course, the big ticket item would be the water needed in all of these process steps. And that's assuming that it would even work in zero gravity. So there you're looking at up to 10,000 times the amount of mass in water that you get from refined gold. And potentially, you could reclaim some of this wastewater, but again, that's only going to be part of it, and that's just going to add to the power and cost and extra mass and equipment that you'll need. Okay, now the situation is already looking pretty ridiculous, but when you factor in transportation costs, it becomes simply impossible. So, for our first example, let's just show Starship. Everybody loves talking about Starship. Basically, Starship alone has about 7,000 meters per second of delta V when it's fully fueled. So if you do orbital refueling in geostationary transfer orbit, you could get up to a total of about 18,500 meters per second. Now, if we go to our delta V chart, you can also see that it takes around 18,000 meters per second from the surface of Earth to get out to the asteroid belt. Now the problem is, of course, you're going to run out of fuel at that point, and then coming back is going to require another 9,000 meters per second of delta V, which is where you're going to have to start using rocket staging to fix that. So you might be saying, what about near-Earth asteroids? Aren't they closer? Don't they require less delta V? Well, it's not always the case, and a lot of near-Earth objects actually spend most of their time out in the asteroid belt. So when I looked up some near-Earth objects that were M-type asteroids, the first one that showed up was this 1986 DA. And when you do the math, getting out to this orbit actually requires more delta V than getting to a normal asteroid belt object like Ceres, for example. So this is showing the Psyche spacecraft, which is visiting an M-type asteroid in the asteroid belt, and this is a mission by NASA. And you can see it actually requires a gravity assist from Mars, and they're also using electric thrusters the entire time. And this is more efficient than a chemical thruster like on Starship. And you can see here it still takes over 6 years to get to Psyche, and they actually have no plans to bring it back. So there's not even enough delta V to come back after this mission. Okay, so moving on. It is technically possible to get there with Starship, and I'll explain how. So first thing you're going to need to do is launch about 50 refuel flights to fully load up Starship in geostationary transfer orbit. Okay? And then it's going to have just enough delta V to make it all the way to the asteroid belt. Okay, now if you account for all the costs, this is being really devil's advocate and really generous, but really the bare minimum is going to be over $1 billion, maybe $1.3 billion. And of course, it can be over $100 million just for the fuel alone. And then you're going to need to expend a full Starship and a mini Starship. Okay, so once you get there, of course, you'll be running out of fuel. And so there you can release your 100 tons of payload. Now, using the same mass fractions to get the 7,000 meters per second of delta V, you're going to end up with only 6 tons of payload on that mini Starship. Okay, now 6 tons of the normal ore on these asteroids will be only worth about $12,000. And in the hypothetical situation where we could just have a giant gold nugget, it would be worth $350 million. So we could fly our mini Starship back to Earth, and then it'll run out of fuel. We can transfer to another ship. And in the end of the day, you're looking at only a revenue there of around $300 million. So you're end up going to be losing almost all of your initial investment. So it's completely impossible to use Starship. Now you're probably asking, what about electric thruster? What about using a more efficient platform? Well, in this case, you could actually launch a spacecraft that's sort of like the ISS, but it can have the same mass fractions as Starship, but use a Hall effect thruster, for example. And if you do this situation and maybe you assume some gravity assist from Mars or Earth or Venus, then you can maybe get out to about 30,000 meters per second, maybe a little bit more. And you can end up doing round trips with about 100 tons of payload. Now, of course, this would still require about 15 orbital refueling flights from Starship, and you need to build this giant space station or spacecraft. So it's really going to be costing you $2 billion. Again, this is super, super generous. If we were to do this today, it would probably be more expensive than SLS, I can guarantee. So maybe like 30 billion, for example. But let's just be nice and assume it's 2. So of course, if you mined normal nickel ore with this, or iron nickel ore with this, you'd be losing about $2 billion, making almost no money. However, if you could magically get refined solid gold, then yeah, you could make a profit, and actually you can make up to 15% per year. So this is something that someone could actually want to invest in, again, assuming you could just magically get refined gold. In reality, like we talked earlier, we're actually going to need mass fractions and ratios of about 1,000 to 1 for equipment, and then 1,000 to 1 for chemicals and explosives and things like this, like consumables. Okay, so here you're looking at about 16,000 Starship refueling flights, and you need about 1,100 of these giant spaceships. And when you include, the fuel, the extra mass that you need to produce artificial gravity, and so on, research and development, really the long term, I'm thinking even thousands of years, you're really looking at $4 trillion of what we consider money today. Okay, now when you add up 100 tons of solid gold, you end up with about $6 billion worth of gold. Now, you subtract minus 4 trillion, which is your costs, and you're going to end up losing minus $3.994 trillion. Okay, so you're going to be losing 99.85% of your initial investment, and no one's ever going to do this. Again, this is the best case scenario. I've been really nice with all of my assumptions, and so yeah, really this is a total disaster. Okay, guys, so in conclusion, asteroid mining is a total joke, and it will really never happen ever. unless you're just mining to get materials to sort of settle on an asteroid, which is a totally different thing. Now, I haven't looked into any of these asteroid mining companies, so maybe I'll make a video about that. I'm sure most of them are total frauds, and I think that would be really fun. So let me know what you think. And thanks so much for watching, and make sure to like and subscribe, and then let me know what you think in the comment section below. Have a great day.